Good afternoon again. Okay, now we're getting into the meat of things of part 8. We're looking at the conservation of linear momentum. So I mentioned in the first video on part 8 that linear momentum is a quantity that is conserved when there's a collision. Of course, there's a small caveat to that. It's conserved when there are no external forces acting on the whole system. When everything is closed and isolated. For all of our purposes, all of our examples, we'll consider our systems to be closed and isolated unless specified. If we specify that there's an external force acting on the thing, then that goes out the window, but let's not. Much like we wrote earlier the conservation of energy as delta E is equal to 0, well, the conservation of linear momentum is very similarly written. That's it. Though that P here is really the total linear momentum. Change of the total momentum of the system is 0. If you prefer, this is another way of writing it. Before the collision, after the collision, total linear momentum. Note the vector equation is the same. Again, since this is a vector equation, we can split it into its components. But again, because of the circumstances of this winter 2020 semester, we can ignore the other two components and we'll focus only on collisions in one dimension. Whether the dimension is x, y, or z, it doesn't matter, the math is the same. The subscript is the only thing that changes. If we had a collision of 2 dimensions, or if this was a regular semester, we would look at collisions in 2 dimensions, but ignore things in 3 dimensions because again, if you can do this in 2 dimensions, you can do this in 3. We mentioned collision. We mentioned that there is conservation of linear momentum if there is no external forces acting on the system. But now, how can we be more specific about the types of collisions that we have? Because of course, there's not only just the one type of collision that would make things too simple. So these 3 types are elastic, inelastic, and completely inelastic collisions. Each of those has a specific set of conditions before and after the collision, to the states of the objects before and after the collision. The first one, elastic collision. It is a case of a perfect world, which, as we know, doesn't exist. But even if it's never seen in real life, some things can be approximated to be elastic collisions, and so it's worth studying them. An elastic collision has 2 characteristics. As always, the change in linear momentum is 0, but also the change in total kinetic energy is 0. Think of 2 billiard balls. If you've played pool, you'll probably have experienced this at some point. The perfect shot, where you line up your cue ball and your stick perfectly so that the next ball, say the 8, goes into the pocket. 8 is here, cue ball is here, hit. Perfect transfer. The cue ball stops moving right after the collision. That is an approximation of an elastic collision. All of the kinetic energy that was in the cue ball is transferred to the 8 ball after the collision. The momentum is conserved because it's a collision, but before and after, the kinetic energy is conserved. In real life, of course, that doesn't happen. There's a small loss of energy, of kinetic energy, due to the deformation of the 2 balls that's then transformed into thermal energy and whatever else. But for this case, 2 cue balls, we can ignore that. Change in linear momentum is 0, 3 dimensions. For our purposes, 1. Change in kinetic energy is 0 again. Before and after, we have the same linear momentum and the same kinetic energy. The second type of collisions are inelastic collisions. These are what everyday life collisions are. Again, there are 2 conditions for this. One is the change in linear momentum is 0. The other is that the change in kinetic energy isn't 0. And that's really the only difference in between the 2 types of collisions, elastic and inelastic. In one, the kinetic energy is conserved, in the other, it isn't, because deformations happen. This is the more general case. The other 2 are specific case of this one. A completely inelastic collision happens when one object suddenly becomes 2 objects, or when 2 objects suddenly become one object. Think of, drastic example is two cars colliding in an accident and fusing together. Or if you were to throw a ball of Play-Doh at another ball of Play-Doh and they become stuck together afterwards. Those are completely inelastic collisions. We can also think of literally an explosion where something is, for example, static and breaks up into many, many pieces. That is an inelastic collisions as well. Because they're collisions, the change in linear momentum is zero. Because they're inelastic collisions, the change in kinetic energy is zero. And that's it. This is the conservation of linear momentum, and we apply it into one of these three classes of collisions. The rest is just application of this. The warning for this section is that the algebra can be very delicate. We need to be careful about how we place our axis and which direction we specify as being positive and negative. Often I'll take positive x, positive y, the usual. Sometimes it might change. Since we're going to be focusing on collisions in one dimension, a positive direction of momentum or of velocity will have a positive sign associated to it, and a negative direction of velocity or momentum will have a negative sign associated to it. That's it. Now go practice, and I'll see you in the next one. Take care.